Okay.
Okay.
Under sign off. Okay.
Cool. All right. Yeah. So hi everyone. Again, we're back. We're going to talk about inferencing on Bayesian networks with sampling methods, as the title says. Just a few things that I did want to point out before we start. First of all, this lecture is going to be fairly fast. There's quite a lot of content. I noticed that in the last two. So if you do want to watch it later, feel free to put it on 0.75 speed. Just one important note I'm going to mention is about technology. This lecture is also using quite a bit of it. So if you notice at any point that the screen is frozen or anything, just let me know immediately so that I don't stick around, although I should be able to see what you're seeing right now too. All right, so let's get started. So thus far, you've talked about, Bayesian networks, and you've talked about inferencing on Bayesian networks, but we've only kind of talked about one way of doing it, and there's many different ways of doing it. In particular, you've talked about exact methods, but we're going to talk about approximate methods. And that sounds kind of dumb, like why would you want approximate methods if you have exact methods and those seem to be working? But hopefully, at the end of this 50 minutes, we will answer that question a little bit more. So let's start with a Bayesian problem that we can work on, something simple. So to that end, let's suppose there's a farmer and this farmer buys a new smart sprinkler, right? Everything is smart these days. So they buy a new smart sprinkler and it's supposed to water his crops when it doesn't rain, right? So when it's not raining, it waters the crops. When it is raining, it doesn't water the crops. Pretty standard. Now the sprinkler comes equipped with a daylight sensor, so that's how it kind of knows something about the world. In particular, it lets it know if it's cloudy or not outside, right? And it uses that information. So it's programmed to water the crops only if it's not cloudy, right? Because if it is cloudy, it's most likely going to rain, so it won't water the crops. But the sensor isn't perfect, right? And the farmer doesn't want his crops to be overwatered. Now, to emphasize this idea of the sensor not being perfect, it's important, right? What I mean in a loose sense is that it doesn't always work exactly as intended. So if C here is kind of the event of it being cloudy outside, and let's suppose it is cloudy, well, we expect the sprinkler to not turn on, but it will turn on with a probability of 10%. So not often, but it still will, right? Similarly, if it's not cloudy, we expect the sprinkler to turn on, but in this case, it's only going to turn on 80% of the time, right? So it's pretty good, but it's definitely not perfect. And this is where the probabilistic aspect comes into play. So in order to get any further, we'll need to create a Bayesian network. And to do that, we'll need to identify some causal relationships between the variables at play. And this is kind of an art, but the way we're going to do it is like this. We're going to start with crops, right, which is what we care about. We want to make sure our crops aren't overwatered. And what does that depend on? Well, it depends on the sprinkler turning on or not, but it also depends on other things, right, like whether it's rainy or not. Right. And both of these things themselves aren't independent and in a vacuum. They also depend on other things, like it being cloudy outside. Right. And of course, you could consider many other things, like you could consider what season we're in. You could consider where in the world we're in. I'm not going to do that because I want to keep it relatively simple and straightforward, but you could do that. That's the point. All right. So we have these variables. Let's now just take these variables and just give them names so that it'll be a little bit easier to work with. In particular, the first one, we'll call it cloudy. We'll refer to this one as rain. We'll refer to the one on the left as sprinkler, and finally we will refer to this fourth one, the crops, as ground, because I'm really interested in the state of the ground, which I guess is analogous to the state of the crops. Okay, so we've cleaned up that network, and this is what it looks like. Are there any questions thus far of us building our network? Okay, so let's move on from that. Let's just talk about really quickly the domain of each of these variables, right? So in particular, let's start with cloudy. So cloudy is a yes/no variable. It can be cloudy or it can't be cloudy. Right, same with rain, it's either rainy or not. For the sprinkler, it's also a binary variable. I'm just going to use on/off here because I think it's just a little bit more intuitive to refer to it that way. The ground, though, it's not a binary variable, at least in my definition. It's going to be a trinary variable. It's going to have three components. It's going to be either dry, right, damp, which is slightly wet, or wet, which means really wet, right? We don't want it to be the third case because then our plants will kind of die. We don't want it to be dry either. Ideally, we want it to be damp. And that's really just, I'm putting this here just to emphasize the fact that, these variables can be non-binary, right? They could be a lot of different things, and so that's why I put it in here. But you could really define a lot of these things any way you want, right? You could have 4 states for your ground. Doesn't matter. Okay, so now that we have the domains, we'll need some probabilities on these domains, right, to get anywhere. For cloudy, because it doesn't depend on anything, I can just give you one probability. In particular here, I'm going to give you the probability that it is cloudy. And it turns out that I'm just using 50%. Where did I get these numbers from? I don't know, but we'll just go with that. For rain, rain is also a yes/no variable, but it does depend on cloudy. So when I give you the probabilities, I need to give you the conditional probabilities with respect to the cloudy variable. right? And so here what I'm saying is that there's an 80% chance of it being rainy given that it's cloudy, and a 10% chance of it being rainy given that it's not cloudy. Of course, there's two other probabilities here, which are the case where it does not rain, but you know that you can just get that by taking the complement of these two values, right? 1 minus 0.8, 0.2, 1 minus 0.01, 0.9, right? So I'm not explicitly providing it here. All right, same thing for the sprinkler, right? Just different probability, so I'm not gonna go over that, but same idea. And for the ground, it's gonna be the most complicated one, not only because it has 3 potential states, but it also has 2 parents, right? 2 things that it's connected to. So in total, I have 4 possible cases for the parents, either on yes, on no, off yes, or off no. And for each of those, I have 3 probabilities that I technically need to give you. The case where it's a dry, damp, and wet. Again, I'm not providing you the case where it's wet because you can just compute that from the other 2. Any questions at this point? Okay, so that's basically, we've set it up. And at this point, the farmer wants to know how likely it is for his crops to be overwatered if it rains, right? Given that it's raining, how likely is it that his crops are overwatered? And by overwatered here, we mean that the probability that the ground is wet, right? So we want to know the probability that the ground is wet given that it rained. Okay, so we want to know about these 2 variables, and the way that you've learned about how to do this thus far is using variable elimination, right? And I'm not going to provide a solution here for the variable elimination, but I do want to just kind of set up what the process looks like again, just to remind you, so that you can kind of, 1, remember what that looks like, but also 2, we'll be able to compare it to the way things work when we're not using variable elimination. So at this point, can you all see like the slides? I just need some sort of indicator from someone.
Yep, that's good.
Okay, perfect. And open up this. And there we go. Okay, so you should all hopefully see a whiteboard at this point on the right-hand side. And I'm just gonna kind of talk you through the process of how variable elimination is working, right? So if you recall, the basic idea was that we wanted to figure out the probability that the ground is going to be wet. So let me just redo this one more time. The probability that the ground is going to be wet, right? Given that it is raining. And we know that we can just compute that using effectively the joint distribution, ground and rainy, divided by where we take that same joint distribution, but we consider all of the cases where we go through all of the different cases of ground, right? And in this case, this should be rainy equals yes, and ground equals wet, right? And same thing here for rainy equals yes, right? So we know that we can do that. And at this point, what you see is that effectively everything depends on the joint distribution. So once we can compute the joint distribution with the ground and rainy, we can compute everything. Right, so I'm just going to focus on that for a brief second, where we're just worrying about the joint distribution. So to compute the joint distribution, P, G, and R, we know that, well, what we could do is, we don't know that directly, but if we look at the Bayesian network, we do know the probability of G, R, S, right? And what's the last variable? C for cloudy, right? And all we have to do is really get rid of the variables that we don't care about, which are nothing more than the sprinkler and cloudy. Right, so we're just summing those up. This is what we do when we say variable elimination. We're eliminating those variables. And of course, this probability here, you can just express it as a product of 4 probabilities using the causal relationships on the left-hand side that you see. Right, in particular, we can start with cloudy because it depends on nothing. Then we can go to rain, let's say, probability of rain given cloudy, probability of sprinkler given cloudy, and the probability of the ground given sprinkler and rain. And then the last thing you did at this point, I know it's a little cut off, apologies, but the last thing you can do at this point is you break up this sum into multiple sums. You start moving things around, things that don't depend on other things. You actually go through the process of evaluating this, and it's a pain, right? It's not easy, even for something as small as this. It does take a lot of effort. And if you do all of this, right, and you compute the joint distribution, and you compute the sum at the bottom, the normalizing constant, and you evaluate it all, and you get it right the first time, you will find that the resulting probability, according to the probability distributions that I've given you on the left, is approximately 19.68% for this probability. That's what you will find. Now, if you're interested in looking at that full solution of how we got there, I've already posted it in a previous announcement. You can take a look at that, but I'm not going to fully derive that here because that's not the point. But that's the point that you will get. You will get about 19.6. All right, so let's go back. And so we've concluded, apparently, that we are going to get 19.68%. Again, you can verify that, but I won't do it here. But now, let's consider doing the same thing using an approximate method, in particular, sampling. Okay, so again, we want to figure out the probability that the ground is wet given that it's raining, right? So what we can do is we can sample the state of a node using its probability table. And the same idea applies with other things. So for instance, let's imagine you wanted to figure out the probability of a coin landing heads. Suppose you didn't know that probability, what's one way you could figure it out? Well, you could take that coin, you could flip it 100 times, 1,000 times, and you could see how many times did it land heads out of the total number of coin flips. It's kind of the same idea that we want to do here. We want to see if we can somehow simulate this network, simulate all of these variables, and get a sample, right, a coin flip, and keep doing that over and over and over again and see how many of those samples match what we are looking for, right? So that's kind of what we want to do. It's just a little bit more complicated here because it's not just as simple as a coin flip. There's many variables at play. So let's start with a simple variable. In particular, let's start with cloudy. Cloudy depends on nothing else. So we can actually just sample it without needing to do anything. We can just do a coin flip. In this case, literally, right? Because the probabilities are 0.5. So I could just say, okay, let's flip a coin. If it lands on heads, let's say it's cloudy. If it lands on tails, let's say it's not cloudy, right? But for something else like rain, it's a little bit more complicated, right? Because though the probability of the coin kind of depends on whether it was cloudy or not. So in order for us to decide, hey, how biased is this coin? We need to actually know whether it was cloudy or not. So the point that I'm trying to make here is that we need to know the states of the parents in order for us to be able to say anything about the child, in order for us to be able to sample the child. Does this make sense? Please let me know if not. Okay, cool. Yeah, so we need to be able to sample the parents. Okay, that's an important point. So now let's consider an algorithm that can actually sample an entire Bayesian network. Again, we want to start with the thing that we're after. What are we after? Well, remember, we wanted to know the probability of the ground being wet. So let's start at the ground. In order for us to figure out the probability of ground, in order for us to be able to sample ground, we need to know the states of its parents. So in particular, we need to know the state of sprinkler and rain. So let's start with sprinkler. We need to know the state of sprinkler. In order for us to know the state of sprinkler, we need to know the state of its parents. So cloudy, right? But cloudy depends on nothing else. So now we can immediately sample cloudy. And let's suppose I flipped that coin and it gave me yes. So it is cloudy. Once I know that, I can now go back, I can backtrack and I can sample sprinkler, right? I can decide, okay, well, it is cloudy, which means which distribution am I going to use on the sprinkler side? I'll use the first row, right? Because it was cloudy. So I'm going to flip a coin where it's 10% likely that the sprinkler will turn on. So I flip that coin and let's say, I suppose I get that the sprinkler was on. Now we backtrack to ground, but we're not done, right? Ground needs to know another parent's value. So we go up to rain, we sample rain, but in order for us to know rain, we need to know cloudy. But in this case, we now already know cloudy because we've sampled it before. So we'll just use that same value of cloudy and we'll sample rain. Maybe we get yes for rain as well. And now that we have all of the parents of ground, we can finally sample ground. And maybe once I sample it, I get wet. So what have I just done here? We have created one sample at this point, right? The sample was ground equals wet, sprinkler is on, rainy is yes, and cloudy is yes. This is equivalent to doing one coin flip, right? All we've done is do one coin flip. Now we need to do this many, many, many times in order for us to have anything useful. So to infer, as I said, we'll need to have a lot of samples, right? So let's suppose we have 10 samples, and let's say those 10 samples look something like this. I just pulled this out of nowhere, right? So where are these coming? I just made these up. But let's suppose these were the 10 samples that we saw. In order for us to estimate the probability that the ground is wet given that it rained, well, we can first consider the samples that are consistent with the evidence. So let's look at only the samples where it did in fact rain. That's these ones, right? Once we've done that, let's look at those samples, the ones that are still dark, where the grass was actually wet or the ground was actually wet. So those are these ones, right? Now, how many of those samples was the ratio, right? We're trying to figure out the ratio at this point. So let's just figure out that ratio. So it looks like 3 out of 5 satisfy the condition that we needed. So we'll say that the probability is 60%. Okay, so that's basically it. That's really how inferencing via sampling works. But at this point, it's not really useful unless we can actually kind of code it up. So I want to try something, and we're going to try coding it up within 30 minutes. Now, again, this is why I say that this lecture is going to be kind of fast. So if you don't understand every little detail, that's fine. You can rewatch it. But I just hope you get the main idea. That's really all I want you to take away from it. So can you guys see the coding window? Perfect. Okay, so let's get started. The first thing we kind of need to do is we need to represent a node. But before we do that, I'm going to use, we're working in Python. I'm going to use numerical Python as a library just because I need to use it for a lot of my arrays. And I'm also going to import a random library because I will need to be able to make random samples. That's all I'll need to import. But at this point, I'm going to actually start writing some code. So let me just close the terminal window and we'll start writing. The first thing we need to do is we need a way to represent our nodes, right? The nodes on the left that you see 4 nodes, but we need a way to represent them. And now, one thing that I do want to point out here is that in order for us to have a nice mathematical representation in code, it's good for us to be able to index these nodes with a specific number, right? So in particular, we should say what these nodes are going to be indexed by. So for example, I'm going to choose the index where the cloudy node, or yeah, cloudy is going to be 0. I'm just choosing that, right? And then I'm going to say that the sprinkler is going to be 1. I'm going to say that rain is going to be 2, and I'm going to say that the ground is going to be 3. Why have I've just done it this way. It's up to you how you want to do it, but this is just how I've decided to do it. The other thing is we need a way to index the states of each node, right? And so the way I'm going to do it is I'm going to say that yes or on is going to be 1, and no or off is going to be 0. Okay? So far so good? And the last thing I'm going to do is I need to also define indexes for the ground state, but it's not as simple as yes, no, because it has 3. So the way I'm going to do it is I'm going to say wet is 0. I'm going to say that damp is 1, and I'm going to say that dry is 2. This is just a convention that I'm choosing. You may not like it, and it's up to you how you want to do it, but you just have to be consistent, right? This is the way I'm doing it. All right, at this point, we are ready to actually start defining our node structure. Now, I want to add a little caveat, and that caveat is that this code is going to be incredibly inefficient, right? The reason I've done it this way, though, is to make it clear what's going on. So don't focus on the efficiency, just focus on making sure that you understand what's going on. Efficiency comes later. Right. All right, so we need to define a class to hold our node, right? Our node, which is either cloudy, sprinkler, ground, or rain. So we'll start with the constructor. And what does this constructor need? Well, I'm going to argue that it needs to know the parents, right? I need to know who my parents are. That's one of the kind of properties about myself, and I'm going to argue that that's important. The other thing I need to know is the conditional probability table, right, of myself. What is my conditional probability table? I'm going to call that P. Okay, again, stop me at any point if any of this is confusing, but I'm going to call it P. Now, all I'm going to do at this point is I'm going to start doing some assignments, right? So I'm just going to say, set my parents to whatever you pass in, set the probability distribution to be whatever you pass in. And one other thing that I want to kind of keep track of is what is my current state, right? When we're actually doing sampling, each node is given a state, right? You either say cloudy is either it is cloudy or it's not cloudy. Sprinkler, it's either on or off. So I want to know what my current state is. And for that, I'm just going to create a variable called state. Initially, we're going to set it to none because initially I don't have a state. You haven't sampled yet. But when you do, we're going to update this variable later on. Another thing that I wanted to know is how about how many, or what are the possible states that I could have, right? What is my domain? Remember that before when we were starting off with the original problem, our domain, yes. Don't you need a list of probability, possible values of C? Exactly. Some nodes, exactly. Yeah, you were ahead of me. So we need a possible values of the states. Now, and when we started very back, some were binary, some were not binary. So I need to actually keep track. The way I'm going to do this is I'm going to use a list of indices. So the states for cloudy are going to be something like this, 0 or 1, right? The states for ground is going to be 0, 1, 2. Make sense? Those are the possible states that I could have. They're not the current state, they're just the possible states. So we're going to take self.states. I should really call it possible states, but it's also too long of a word. So we're going to just say the possible states is going to be a range right? And what is it going to be arranged from? Well, it's going to be arranged from 0 to the number of states. So self.num states. Now I haven't defined num states, so I need to actually get the number of states. Now you could pass it in to the init function, the number of states, but I'm going to argue that I can actually just get it from the probability distribution that you've passed in, because using the probability distribution, I can see how many columns you have, and those number of columns will tell me exactly how many states you have, right? In particular, if you look in the columns on the left, what you'll see is that, take a look at the grounds probability table. Ignore the first 2 columns because those aren't probabilities, right? Only the second 2 columns are probabilities. And there is a third implied column that I'm not telling you about, right? The complement column that you can calculate. So the number of states for ground is 3. There are 3 possible states for ground. By the way, in code, the probability distribution table will contain all 3 columns explicitly. Again, you don't need it to, but because I don't care about efficiency and I'm just trying to make it as intuitive as possible, this probability table, this p value here, will contain all 3 or all n columns. Okay, we're not going to make it efficient. So because of that, I can actually derive the number of states directly, right? I can say num states. I'm just going to look at the shape of my probability table, and I'm just going to extract the number of columns. That's all this is doing. Extract number of columns from probability table. That's all this is doing. You don't have to get like lost in NumPy if NumPy is not your thing. At the end of the day, it's just giving us the number of states. Okay, so we have everything we need at this point in the constructor. There is one other thing we need to do within this class, and that's actually define a function that is going to allow us to sample this node, right? So we're going to create a function that lets us sample. In order for us to sample, what did I say we needed? What did we need to know? We needed to know the parents' states, right? We needed to know the states of the parents. Without that, we can't sample. So let's assume that we are given the states of the parents in this list. Okay, once we are given the states of the parents, then we can actually perform sampling. Now, how do we do that? Well, I'm going to argue that all you really have to do is you have to set your state to be a random selection, it's a random choice. This is where I'm using the random library, a random choice of all of your possible states. And what distribution are you sampling according to? Well, you're sampling according to the p distribution that you loaded in. But not exactly the p distribution, right? Because that distribution gives you conditional probability tables for all possible cases of your parents. But we are given a particular set of parents. And so what we want to do is we actually want to evaluate our probability distribution given the set of parents that we have, right? So this line right here is just extracting the row that is consistent with our parents' states. So either if we're looking at the ground, it's either like the first row, second row, third row, fourth row. And then we're going to assign that to be p, and then we're going to randomly sample using that distribution from our possible states. Make sense? I hope this is clear. I know it's fast. Okay. Please do give me some feedback if it's not clear. Okay, so there's one other catch here though, and the catch is that the parent states could be an empty list, right? It can be empty because, well, that's what it means when you are a root, right? Like, for example, has no parents. So what we can do is we'll just need to add a condition to account for that. And I'm just gonna like write it out real quickly. And all this condition is really saying is if the parents list is empty, then you can actually just sample then your probability distribution is a single row and you can sample just with that row. Now you might say, well, do you really need to account for that case? And the reason I kind of do is because NumPy is a little bit weird with indexing when there's only one row and that sort of stuff. Don't worry about those technical details. The key point here is that we are sampling. And if you understood the first thing that I did, the second thing is just a little edge case is all for empty lists. Are we all good? Okay, thank you. So at this point, we've sampled and we've initialized. So let's get out of this node class and let's actually do the inferring. So in order for us to do any inferring, we need to actually define a graph, right? And so the way I'm going to define the graph is as follows. What I'm going to first do is I'm going to actually define all of my conditional probability tables. So let's start with cloudy, right? So cloudy. So this is going to be the cloudy conditional probability table. Well, if we look on the left, what is the cloudy conditional probability table? It's just 0.5, 0.5, right? This is just literally from the left of your screen. And then I'm going to define the cloudy node as a new node. And remember how we defined our node class? It needs to take in the parents first, and then the probability table. Well, cloudy has no, this should not be none, this should be node. But cloudy has no parents, so we'll pass it in an empty list. Okay, and what's the probability table? Well, we've just created it, it's PC. Okay, and at this point, you can do the same thing for all 4 nodes. I'm not gonna manually write it out, I'm just gonna bring it in here because I think that's pretty straightforward to do. You just need to look at the probability tables, slap it in here, create the node with the appropriate parents. The only thing I'll talk about here is the parents list. In particular, if you look at Sprinkler, you'll notice that its parents is 0, right? It says just a single parent, 0. Why is it 0? Well, because remember 0 corresponded to cloudy, and cloudy is exactly the parent of Sprinkler, right? And similarly, the parents of ground are 1 and 2, which correspond exactly to Sprinkler and rain. Again, this is the convention that I've chosen, and I'm following this convention the whole way through, right? That's really important, otherwise you'll get wrong results. Okay, once we've defined all of our nodes, we need to actually establish the convention and code that I just talked about. Thus far, none of these nodes actually know that they are node 0 or node 1 or node 2. So we need to actually establish that. And to do that, what I'm going to do is I'm going to say that my graph is nothing more than a dictionary, where node 0 is going to be cloudy, node 1 is going to be Sprinkler, node 2 is going to be rain, and node 3 is going to be ground or grass. At this point, that's it. I'm done with making my graph. Are there any questions about actually setting up the graph? All right. Let me know if there is, but that's how we've done it. We've made the graph up to this point. Now we can actually do inference on this graph. In particular, we need to write those functions. The first one I'm going to write is a rather simple one. It's just going to be one that resets the graph every time. What do I mean by reset graph? Well, I mean, remember how each node in the graph has a state variable, right? What its current state is. Well, before I sample every time the graph, I want to reset it. I want to reset all of its states back to none so that I can start a fresh sample. So to do that, I'm going to take in a graph. And what I'm going to do is I'm just going to iterate through all of the nodes in the graph. And I'm just going to set that node's state to be none. Simple as that. Okay, reset graph is done. All right, the next thing is a big thing. This is the actual bulk of our inference code. We're going to actually do some sampling. As you might have imagined, this sampling function or this inferring function is going to be recursive, right? Because if you go back to the way I defined the algorithm, we start with ground. We work our way up to Sprinkler, to cloudy, then back down to Sprinkler, to ground, and then up to rain. You almost notice that it is a depth first search, right? In fact, that's what it is here. So it's going to be a recursive depth first search in a sense. And to do that, I'm going to start by defining a helper function, right? Typically writing these recursive functions is easier when you have a helper function that's actually doing the recursing. So I'm going to use the helper function to do that. And in particular, this function is going to do a lot of the actual sampling. What I'm going to do is I'm going to have it take in the node that I want to start from. So in the case of the algorithm example that we started at earlier, that node was ground, right? And I also want it to know the entire graph. Of course, it should know the entire graph. Otherwise, how is it going to sample on the entire graph? Okay, so we have to start with our base case, right? As with usual in recursion, right? So our base case is going to be if the current node has no parents, right? Remember, that's when we stop recursing. That's when we stop our search. So if the current node has no parents, we can sample right away. Right? We don't need to worry about the parent states because, well, there are no parents. So all you have to do is if we check if the graph at the current node, so in other words, we're checking the current node of the graph. If its parents are empty, so it has no parents, then we're in the base case. And what can we do when we're in this base case? Let me just create some more space here. Well, once we do that, we can just sample, right? So we can just take the node at that graph and we can just call our sample function. And we have to give it the parent states, but there are no parents, so there's going to be no states, so we're going to give it an empty list, as expected. Okay, we're done the base case. Now for the harder case, which is the recursive case. How do we do it? Well, before we can infer ourselves, remember that we said that you need to first infer the parents. So first, infer all parents which have not yet been sampled. This latter point, this which have not yet been sampled, is somewhat important. Because remember how when we were explaining the algorithm at the very start, we had Sprinkler, which sampled cloudy, and then rain was also trying to sample cloudy. But we don't want both of those variables to make a new sample of cloudy. We want to use the same state of cloudy, right? You don't want to change the state midway through one sample. You can change the state in a new sample, But when you're doing one full sample of the graph, you need to maintain the same state for all your variables, right? So we want to make sure that our node hasn't already been sampled. So what we're going to do is we're going to go through each of my parents, and you're going to check those parents, and you're going to check to see if the parent has a none state. In other words, has the parent not yet been sampled? If it hasn't been sampled, then we want to sample the parent. How do we sample the parent? Well, we just call this sample graph helper function. This is where we're doing the recursiveness, right? We're going to call the same function that we're in, but with the parent instead of ourselves. So we've now sampled the parent. One last thing that we'll need to do here is we'll need to keep track of the parent's actual states, right? Why? Because when I'm about to sample myself, I need to know the states of my parents. So before starting this for loop, what I'm going to do, I'm just going to create a list of the parent's states. It's going to start off as empty. And every time I do a sample, I'm just going to append to my parent states the state of the parent that I just ended up sampling. Right, so whatever state I just ended up sampling for the parent, I'm just going to append that to my list of parent states. Now, once I've gone through this for loop, I've sampled all my parents in theory. So now I can sample myself. Okay. But I'm just going to do that, right? So we're just going to sample ourselves. So instead of graph.parents, we're going to do graph.node, which is the current, and we're going to sample it. What do I need to pass in? I need to pass in the states of the parents, and that's why I had to keep track of them, right? Because now I can pass in the parent states that I just created up here. Fine. There's just two other condition things that I want to add here to make this a little bit more robust. The first thing is I want to add an if statement that actually checks whether the current node has been sampled or not, right? It's fine if we don't really add this, but I just want to be extra sure that the current node hasn't been sampled. So I'm just going to add that check to be doubly sure. The other thing is that the way we've defined it and the way NumPy works is that this list here actually needs to be a tuple. You don't need to worry about that right now because that's a technical implementation detail, not an algorithmic detail, right? So just accept that this needs to be a tuple, and when you look at the code later, you'll probably understand why that is the case. Okay, so this code is and has been posted, by the way, if you do want to take a look at it later. All right, that's it. That's our sample graph helper. We are done, right? That's everything that it needs to do, so I'm going to close that off. Are there any questions about sample graph helper? Okay, so the next thing we're going to actually do is we're going to actually sample the graph. Remember, the sample graph helper, what it did was it set the state of every node in the graph. But now I want to actually go through the graph and just say, hey, what is the state? You set it, but what did you set it to? I want to actually extract the overall state of the graph. To do that, I'm going to define sample graph. And it's going to, again, take in the same node that I need to start at, and it's going to take in the graph. The first thing we're going to do is we're going to reset the graph before we sample. This is what I was talking about at the very beginning, that you always want to reset your graph. Then we will sample the graph using our sample graph helper function. And once we sample it, we're just going to go through the graph, and we're going to just keep a list of all of the states. So for every single node in the graph, let's just create a dictionary where we keep track of all of the states, right? So we're just going to say the state of each node is going to be whatever you set it to be in the node, right? Why am I doing this? I'm just extracting the states as a dictionary so that I can print it out or I can use it later. Does this make sense? Okay, thanks for answering. So it does help. Okay, finally, we're just going to return these states. Okay, that's it. We've effectively finished the sampling aspect. Now we have to actually infer, right? So where are we in the code, or where are we in the logic in terms of the algorithm? Well, let me just pull up the presentation again. We are done all of this part. We now need to do this part where we are going to get a whole bunch of samples, and we need to look at how many are successful, how many are there in total, and compute the ratio to get the final result. That's where we're at right now. All right. So let's go back to the code, and we'll do that. Okay, so what we want to do is actually write a function that's going to actually do the inferring, right? So we're going to do infer. What does infer need to know? Well, it needs to know what do you want to infer about. What's the query? In this case, the query is about the grass being wet, right? So how do we want to encode that in code? Like, how do we want to encode the query of grass being wet? Well, the way that I'm going to do it, and this isn't the only way to do it, right? It's just the way that I found to be the simplest way to do it at 11 p.m. when I was writing this code, was to define the query as a dictionary. And in particular, I'm going to say the query is going to be a dictionary where the key tells you which node you care about, right? So if we care about the ground node, what node was that? That was node 3, right? So I care about node 3. And what value, and I know the screen is a little frozen, so I hope it'll like unfreeze in a second. This happened once or twice in previous lectures. So there we go. So yeah, so what node do I care about? I care about node 3, right? So that's the ground node. And what value do I want to check? Wet, right? I want to check whether it's wet or not. And I believe I said that was 0, right? Yeah, I did. Okay, so wet is going to be 0. So that's how my query is going to look like. But in addition to the query, I need another thing. In particular, I need to know what evidence am I given. Right? What is my evidence? In this case, it's rain equals yes. So I'm going to argue that the evidence should also look the same sort of structure, a dictionary, where the first key is going to be the node that I care about, and rain, I believe, was node number 2. And what value do I care about? I care about it actually raining, yes, right? So yes is 1, right? I hope I'm following the same convention that I set out, yes. Okay, so this is the way the query and the evidence are going to actually look like in code, but those are the 2 things I need. Right? In addition to the query and evidence, I just want to have a variable that's the number of trials. I'm going to set it to 100,000, the number of samples that I'm actually going to draw, which is a nice good number as opposed to 10. Right? Okay, so then what am I going to do? I need to keep track of 2 variables. I need to keep track of the number of samples that match the evidence, and I need to keep track of the number of samples that match the query and evidence. Initially, both are 0. Then what am I going to do? I'm going to iterate for the number of trials that I set out, where each time I'm going to sample the entire graph. To sample the graph, I first need to know what node am I starting at. Well, that's going to be given by the query, right? If we go back to the query, it's node 3, so I have to look at the keys of the query, right? I have to take my query's keys, and in particular, which element do I want to access? The 0th element, right? Because the keys is technically a list. Again, this is Python jargon at this point, so don't worry if you don't understand jargon necessarily. But the important thing is that I'm just getting the node here. All this line of code is doing is getting the node that I actually want. Then I'm going to actually sample the graph using my big sample graph function that I wrote earlier that was complicated. And I'm going to sample the graph at that node, and it's going to return me the sample. I need to now check if the sample is consistent with the evidence, and I need to also check if it's consistent with the query. In order to do that, I'm going to write one more function, the last function, I promise. This function is going to check for consistency. Consistent, right? And to check for consistency, it needs to know the query that I'm checking against, or the evidence, really. But I'm just going to call it query because I don't want to write query and evidence. So I'm just going to call it query. And it needs to have the sample that it wants to check for consistency against. How do we know if they're consistent? Well, if every node in the sample, if every node state in the sample agrees with that of the query. So I'm just going to iterate through all of the nodes in the query, and I'm going to check if the node state in the query is equal to the node state in the sample. If they are not at any point, then these 2 are not consistent. Otherwise, they are consistent. That's it. My consistency function is done. Now I can use the consistency function in my infer function. What do I want to know? I want to know if the sample is consistent with the query. Right? But I'm going to start by checking the evidence first, because if you go back 20 minutes ago, that's how we did it, right? So if the evidence is consistent with the sample, I'm going to increment an evidence by 1, because I have one more sample that matches the evidence. Moreover, if the query is consistent with the sample, well, now both the query and evidence are consistent with the sample, so I'm going to increment that variable by 1. And that's it, we're done, okay? That's really all the code there is to it. The last thing I really kind of might do here is I just want to check if my query and evidence, or if my evidence variable is 0, because I need to divide by that. Oh, sorry, I didn't see that question. Can I explain that consistent function in relation to slide list with 10 examples? Yeah, so going back real quick to this slide, and yeah, I think it was already answered in the chat. But effectively, the consistent function is just checking which of these samples are consistent with both the query and the sample. So if you look at the black or blue ones, they are consistent with the evidence, right? Where it is raining, yes to rain. And then the blue ones, right, are consistent with both the evidence and the query, where it's wet, exactly, yeah. All right, so let's go back to the code and let's just finish this off. We're almost done. Right, so the last step here is going to be pretty straightforward. We're just going to make sure that we're not dividing by 0. And then we're just going to get that ratio if we can, right? If we can't, because the number evidence is 0, then let's just return none, saying that we couldn't do it. Okay, that's it. All we have to do now is we have to actually call this, right? So let's determine what the probability is. We're going to say infer. What are we want to inferring? We're going to want to infer our query, which was 3, 0. And the evidence we have to support our query is 2, 1. And then lastly, we print the probability. Okay, we've written our code. That's it. At this point, we are ready to actually do the sampling and actually test this code out. So I'm going to really quickly open up the terminal that I have here. And hopefully you can see the terminal too. You see it? Okay, so we're going to run that terminal. We're going to run this. Oh my God, it has no errors. Okay, so it might take a few seconds, minutes. I don't know. I told you it's really inefficient code, but let's see if it works and what it prints out. Excellent. 0.1984. And if you recall from the, I don't know, 20 something minutes ago, we said that variable elimination gave us 19.68. So looks like it's doing what we want it to do, but you can clearly see how inefficient it is. For a small graph and for 100,000 samples, it took quite a little bit of time. This is not the most efficient way to code it by any means. It's not even close to efficient. In fact, it's as anti-efficient as I could make it to explain the point across, but it does the job. Okay. Any questions on this at this point? All right, cool. So the last thing I want to end off with is just kind of where you go from here, right? So you've understood at this point the basic idea of sampling if you've been following along. But there is a few sort of questions that we could answer. Well, first of all, we see that the two agree. That's great. But there are a few questions, right? The first one is that we have this potential for division by 0, right? Where, oh, if it turns out that you don't get anything that satisfies the evidence, what do you do? Or what happens if you only have a few things that satisfy the evidence? If you go back a few slides, remember how over here we have 10 samples? But only 5 of these samples were actually used because only 5 of them matched the evidence. That seems kind of wasteful, right? No, it's all good. So because only 5 of these are useful, that's a pretty big waste of computational resources. So what we could do is there's this idea of likelihood weighting, and I don't want to get into the extreme details of this right now, but the basic idea is that you force the evidence to happen every time. So in this case, we want it to rain, right? Because that's our evidence. So we will always force it to rain. But if we force it to rain, we're going to bias our samples. So what we do is we're going to assign each sample a weight. And that weight is going to start off as 1. And every time we force a particular variable, we need to account for it by considering the probability of that force occurring, right? So to walk you through that, again, we start at ground. Again, we go to sprinkler. We go to cloudy, we sample cloudy, we resample sprinkler, we get to rain, and at rain, remember, because that's our evidence, we want to force rain. So we're gonna make it be yes, but we're not gonna sample it from the distribution. We're actually gonna force it to be yes. So because we forced it to be yes, we are now going to assign the weight variable to 0.8, because that's how likely that force would have been, right? And we're going to keep doing this every time we sample, and this time around, you will get a whole bunch of samples, but each sample will now also come with a weight. And now what you see is that all of the samples match the evidence. Why? Because we forced it to, right? Of course they will. So because they all match the evidence, we can use all of our samples, but in order for us to infer this time, we don't need to worry about keeping track of which samples match the evidence. Instead, what we can do is we can simply take the total weight of the samples which match the query, right? How many of those samples match the query, and divide it by the total weight of all of the samples, right? So the total weight of all of the samples that match the query are in blue, and I don't know what it is. Okay, I guess it's 4.2. And the total weight of all of these samples is 5. So in this case, it's 84%. And again, these numbers don't align with any of the code or anything else we've done because I pulled these out of nowhere, right? But if you did actually do this properly, it should work out. I'm not going to code this. So I would suggest if you guys are interested to take the code that is up on Quarkus or Piazza and see if you can implement likelihood weighting into that code. It's an interesting thought. And yeah, so that's pretty much it. I mean, you might have a few questions like why do this, right? And a few of the answers for that are, well, if you have a lot of highly dependent graphs and you have limited evidence and you have to compute a lot of factors. You might have noticed this when you were doing variable elimination homework. Moreover, you need to have a good ordering of these factors, and choosing that optimal ordering is not an easy problem to do by any means. And even if you could do all of that, the answer isn't exact anyway, right? Because most likely this is implemented on a computer, which is going to be using numerical algebra as opposed to symbolic algebra. So I mean, really, it doesn't matter, right? And sampling, yeah, it doesn't provide an exact answer per se, but it can as you let the number of samples grow larger and larger. It's fairly efficient, even on large graphs. You can handle more complicated queries than you could with variable elimination. And I mean, the approximation can be made very precise. So I mean, it doesn't matter. All right, so that's it. That's basically where we're at. That's the presentation. I hope you got something out of sampling and you understand that it can be useful, all right, even though it's not giving you a quote unquote exact answer. Source code is available on Quarkus and Piazza. So is the solution to variable elimination if you want to make sure that the 19.68% is correct and I didn't lie to you. But yeah, there you go. Hope you guys found that useful.